Good afternoon, physical geology students. This is the slide that we left off on the last presentation. So we were talking about seismic waves and how we can actually probe the interior of the Earth with using geophysics. And this slide here, we're going to talk about heat within the Earth. And there's several things to talk about. First, the geothermal gradient. And what is this? This is basically the temperature increases with depth in the Earth, and it basically tapers off sharply beneath the lithosphere, and that we know that due to steady pressure increases with the depth as well, and increased temperatures produce little melt except in the outer core. Heat flow, obviously, it's a gradual loss of heat through the Earth's surface, and here's kind of a diagram showing. So if you're closer to a magma chamber, you're gonna have a higher heat flow, and then obviously if you have very uranium-rich rocks, they're going to be giving off radioactive decay, and that's where most of our heat is derived from, is from radioactive elements. And here it's just showing again heat flow is the same for oceans and continents as well. So what we'll do is we'll look at this diagram quickly here, or kind of closely here in the next slide here. So here is temperature versus temperature, and as a function of depth, here's your pressure. And as you can see here, this red line represents the increasing temperatures with depth. So you can kind of see it's broken up. Here's the mantle core boundary right here, and here's the outer core, and then which is liquid, and then you have your inner core here. So as you can see here, where as you increase depth, you increase in temperature. Here's the same thing as well. As you come into the outer core, it becomes it's most likely more dense, and your pressure is increasing, and you're almost at 3 millionths of atmospheric pressure here. So the Earth's internal heat. Here's kind of showing a curve again, showing depth versus temperature, and showing the different colors here. Here you have red, which represents the asthenosphere. You have the outer core, which is represented in the orange, and you have the mantle, which is in this other kind of lighter orange color, and then you have the inner core, which is yellow. And here are some factoids. The crust temperature increases 25 degrees Celsius per kilometer. At the asthenosphere, it's 1,150 degrees centigrade at 1 to 200 kilometers depth. Here's kind of a transition zone, and this is 1,500 degrees Celsius at roughly, what is it? They say 400 to 670 kilometers. That's somewhere here. And then the mantle core boundary is 4,500 degrees Celsius, and the inner core is over 6,000 degrees Celsius. So very, very, very hot. So seismic tomography is another technique that they use to kind of image the interior of the Earth. And these two diagrams down here kind of show that. Essentially, you can think of a seismic tomography as like a CAT scan of the Earth. These hot regions, the hot regions are represented by red, and the blue are the cold regions. So as you can think, you're gonna, wherever you have a tectonic boundary is where you're gonna have most of the reds, and the areas where it's inactive and there's not a lot of tectonic movement, it's gonna be kind of your blues or your cold areas. So this is kind of the interior of the Earth. This is a seismic tomogram, and where do we have more evidence? Again, when we look at all the tectonic map, you can see this is the Ring of Fire, and it outlines the red zones. Basically, outline where the plate boundaries are, and these are the interior of the continents or the cratons. So what I'd like to do now, I'd like to touch on I'm going to get into a little bit of paleomagnetics and talk about the Earth's magnetic field and kind of the fundamentals, what we know about it, what's happened in the past, and we'll go from there. So we know that the Earth is surrounded by a magnetic field. We know that this field has a north and south magnetic poles, and over here it's showing the north and south pole, and basically our field lines emanate from the south and kind of wrap around to the North Pole like this. Here's the geographic North Pole, and here's the North Magnetic Pole. And the geographic north is the one that basically is always changing, or it's migrating. And when we take our compass out, for example, I have my Brunton compass. Let me get my Brunton compass quick here. Where is it? Okay, so here, a geologist never leaves without his Brunton compass. Remember I showed you guys what this is? And so basically this compass will detect the magnetic field. And also the rocks that are magnetic will record the orientation of the magnetic field at that time. As it cools, it's going to lock in that magnetic field orientation at that time. So there's also has been magnetic reversals in the past, and this is where we, like I was showing you here, the lines emanate from the south to the north. Well, what happens is the magnetic field it reversed itself, and what was happening is the field lines came from the north, and they then came to the south. And this is shown right here. It's shown here's a normal polarity, and here's a reversed polarity right here. And obviously the rocks that were forming at that time recorded this change in magnetic reversal. And it's occurred, many times in the past. We don't know why these magnetic reversals really happen. But the next magnetic reversal, your compass will point toward the south pole, not the north pole anymore. And the study of magnetism of these rocks is all about, the discipline is called paleomagnetism, and it's the study of ancient magnetic fields in rocks. And you can reconstruct plate motions over time, which is a really interesting field. So the Earth's core and magnetic field, people ask, well, how do we create this magnetic field? Well, you've got two components. You have the liquid outer core, and then you have the solid inner core. And this churning or rotation produces the magnetic field. And then, obviously, I talked about plate tectonics throughout the semester, and what is the dynamo, or what causes these plates to move, is this internal heat. And this is mainly from radioactive decay of materials. But if our engine, if we lost heat, our engine, the tectonic, everything would shut down. And a lot of these planets, I know Mars, for instance, was a planet that was very similar to ours, and it had water. It may have also had plate tectonics, as well. But the magnetic field here is aligned with the rotational axis. Here's the magnetic north pole, the mantle, the outer core, but it's that turning that creates the magnetic field. So then there's also things called magnetic anomalies. And what is an anomaly? It's kind of it deviates from the average, decrease in strength or increase in strength. So it's kind of an anomaly, or kind of an unknown. And we get magnetic anomalies. And we can measure the magnetic field strength with a magnetometer, and we can measure those. There's like handheld. It's kind of, when you went to Cabela's and you went and got the magnetic detector, that detector is kind of a magnetometer, and it detects iron, and you go around the beach and you look for coins and whatnot. But they've made more sophisticated ones where you can locate these iron ore deposits, So a lot of times, if you want to be a geologist, you work for a mining company, you'll go out and you'll explore for these deposits, so you can refine them and you can extract the metals out of them, to build cars or whatnot. So you can essentially you can locate these by using a magnetometer. And on your right here, it's showing basically this is the magnetic field strength, which is this is increases and it decreases. So let's say you have some magnetite or some iron ore deposit in this rock layer. What will happen is that magnetometer, when it graphs it out, it's going to graph out this basically this symmetrical kind of bump that represents a positive magnetic anomaly. And over here, you may have maybe, let's say, a dike or some rock layer that's really enriched in iron. It's going to also show you an increase in a magnetic field strength. And down here, it shows basically granite, kind of an intrusive kind of body pushing up on these other layers. And it's not as granite doesn't have a lot of magnetic minerals in it, but it shows a very slight kind of subdued kind of strength here. And then on the other hand, if you have nothing, if you have no magnetic materials in it, and you just have sediments, it's going to give you kind of a negative anomaly. So that's kind of how we use magnetometers to detect kind of really high magnetic strength in rocks. And here's kind of just showing again the magnetic field. That's right now it's coming from the south to the North Pole, but I guess we are due for a reversed polarity. So. All right, I'll stop here because I'm over my time. So we'll talk about how these magnetic minerals, record the direction of the Earth's magnetic field. All right, thanks. We'll talk to you soon.